Hello everyone, welcome to Vibrations in Acoustics, or in this case, differential equations. What I'm going to do is I'm going to solve this this non-homogeneous ordinary differential equation for you. I'm going to use a few equations that might be kind of foreign to you. I'll try to explain them the best I can, but a few of them I talk about in other videos. So you may just have to do a little bit of research to figure out what I'm doing, but I'm just going to basically cruise through this example. Alright. So when setting up an ODE, what you need to do is take this equation and basically break it into its most fundamental aspects. So any ODE goes A times x double dot plus B x dot plus C x is equal to A, or in this case, sine of omega t. So this is the basic format of this equation. And if you want to look at sine in a kind of way, you can also, in a different kind of way, you can also say it's the imaginary part of AE alpha t, or however you've done that, because in sine, let me grab the correct equation here. There's the equation cosine of some value, we'll call it A, plus j sine of some value, we'll call B. So this is the imaginary part, and this is the real part. So, if you haven't been introduced to that before, this is something we'll kind of use in this problem. Just something to think about when you see, oh, I have this equal to sine. I'm dealing with an imaginary part of some function. And then you want to put in these coefficients because we're basically going to assign these values. So then in this case, A is equal to 1 because there's basically no coefficient. B is equal to 4, C is equal to 4, A is equal to 1, and omega is equal to 2. These are also really valuable in vibrations, of course, because this is the amplitude and this is the frequency. Alrighty, so now we rewrite this equation again as a characteristic equation, plus 4 squared lambda plus 4, which is equal to 0, where an x dot is equal to a lambda. Each dot is related to a lambda, and it's basically just a placeholder. So if we factor this, you get lambda plus 2 squared is equivalent to that. So finding the roots then, you end up with lambda 1 and 2 equal to negative 2. So if you haven't been introduced to this, this means you have a multiplicity of 2, which defines what we're going to do in this next step. Here, let me change my camera a little bit. I've got a bit of fuzz. It's not very well focused. Okay, try that. That's a little bit better. So multiplicity of 2, which helps to define the next equation. So for the homogeneous solution, homogeneous solution, however you pronounce it. Okay, so we're going to go x sub h of t is equal to e of negative 2t of c1 plus c2t. Okay, so what did I just do? Well, the negative 2, the fundamental equation for this, since we have a multiplicity of 2 real identical roots, there's a equation that you automatically jump to when you have 2 real identical roots, and it is the equation of c1 plus c2t e to the lambda t, where lambda is the value of the root of one of the identical roots. So right here we took negative 2, which was our lambda, put it in here, and then we have c1 plus c2t. Now, multiplicity, the multiplicity is what brings in the 2. Since we have 2 identical roots, you have c1 plus c2 with the t added on. The multiplicity of 2 adds in that extra t. If you had a multiplicity of, say, 3, then you would add on to the side here plus c3t squared. And it would go on from there based on the multiplicity. So this is why this is important. If your instructor hasn't presented that to you, he's probably not going to ever quiz you on it, but it's something to know for future reference. Okay, so now you have the homogeneous basic equation set up. From there, you can just let it sit. Now we have to find the particular solution, because since this ODE is non-homogeneous, it's not equal to 0, you need to solve it out. Okay, so the particular solution then. Particular solution. Solution. What you have to do is, again, this is going to be a foreign kind of equation to you. But since we're working with the imaginary part of this ODE sine, there's an equation that you're able to pull that automatically sets this up again. And this equation is a over square root of b sine of omega t minus a tan of b omega all over c minus a omega squared. And bracket, bracket. Okay. This is the equation you get to pull from. Now, this piece right here is related to imaginary coordinates, where you have some alpha, basically, and it is equal to c minus a omega squared b omega. So this entire equation, this little chunk right here, is the equivalent of alpha. Something to realize, I talk about this more in another video, so I'm not going to go into it a lot right here. But basically, you can just grab this equation because we're working with sine and solve the particular solution from there. Okay, so the value of b is just a side of this triangle. It's actually the hypotenuse. So in solving for b, you just go c minus a omega squared plus b omega squared. And if you look at this, this is just a squared plus b squared is equal to b. And you can take square root of b, or say one of those. Okay. Is equal to b squared. And then you take the square root of b and you get what you want. Okay, so if we solve this out, we have c, a, and omega, all from up here. I'm going to go ahead and sub these into this equation. You get 4 minus 1 times 2 squared plus 4 plus, or no, times 2. Hang on here. 64 plus, yes. 4 times 2, yes, squared. Okay. So, solving this out, you should get b is equal to 64. So then the square root of b is equal to 8. Now, I know that I basically just kind of skipped a bunch of steps, but you're just going to have to take my word for it right now because I don't have enough time to explain this without making an incredibly long video. So check my other videos on this and just research this equation, and the explanations for why this all works out the way it does will become a little clearer. Okay, so now we need to actually solve for the alpha right here, and obviously we have this equation, so I'm going to solve for alpha over here. Alpha is equal to a tan of 4 times 2 all over 4 minus 1 times 2 squared, which basically goes to 0. And if you have an a tan 2 of a number over 0, it is automatically equal to 90 degrees. But since in vibrations we always work in radians, this is going to be equal to pi over 2. So we have alpha and b. Now we can figure out the final part of the particular solution. Let me pick up right here. So then xp of t, the particular solution, let me move this down a little further, is going to equal 1 over 8, because a is equal to 8 from earlier. The main amplitude is equal to 8 from right here of the sine. 1 over 8 sine of 2t minus pi over 2. The 2t was the omega again that we pulled from earlier, and that's that. So now, to get x of t, you add the homogeneous plus x of p. And both of these are of t. If I forget an of t once in a while, it's still there, it's just not really necessary. So we have this equal to e to the negative 2t of c1 plus c2t plus 1/8 sine of 2t minus pi over 2. That's x of t. So we're 3/4 of the way there. We just now have to solve for C1 and C2. We were given initial conditions. Here, let me move this up a little more. The initial conditions of x1 and x2. So we just solve for C1 and C2 using those initial conditions. So we've got C1 plus 1/8 of sine negative pi over 2 is equal to 1. So of x of 0 equal to 1. If t is equal to 0, then this cancels out. Then this goes to 1. Then this right here, this cancels, and you get negative pi over 2 equal to 1. Solve this out, you have C1 is equal to 1 plus 1/8, because sine of negative pi over 2 is equal to 1, is equal to 9/8. So that's C1, equal to C1. So then at x dot of 0 equal to 0, we actually have to take the derivative of this equation now. And if you do that, you get negative 2e to the negative 2t of C1 plus C2t plus e to the negative 2t of C2 plus 2 over 8 cosine of 2t minus pi over 2. Okay. Whoops. It's not very clear. 2 over 8 of cosine. And the 2 is the derivative of this 2 in here, through here. So it's a combination of power and product rules. Okay, so then x of 0 is equal to negative 2c, subbing in 0 for t into this equation, 2c1 plus c2 plus 0 is equal to 0. So then c2 is equal to 2c1, which is equal to, you can go 2 times 9 over 8, which is then equal to 9 over 4. So then your final solution is equal to 2e to the negative 2t of 9 over 8 plus 9 over 4t plus 1/8 sine of 2t minus pi over 2. And that's how you solve a simpler ODE. These can get a lot nastier depending on how much you have to do. But basically, you go through, you find out whatever information you can from the ODE, set it up, get it listed out, find the characteristic equation using lambda, find the roots. Then you, based on what the roots are, based on the multiplicity and that kind of thing, you figure out what the homogeneous solution is. Then you go into the particular solution, and you can use equations based on what the output of the equation is. And this is really the hardest part, is finding out which is the correct equation. And then from there, you can basically just solve for the constants, keep on solving, use the initial conditions to solve for the constants, go through and plug all the numbers back in. And that is your final answer.